particular video, we have a system of two blocks here, M1 on the left, M2 on the right, and it is wrapped around a pulley which has a mass of 5 kilograms and a radius of 0.1 meters. If you need to, pause, read. All right, let's go and crack it out. Part A wants us to find the amount of time that it takes for M1, which is the block on the left, to hit the floor. So let's go ahead and do that. To do this, I'm just going to go ahead and start with my kinematics. I'm going to start with my delta y is equal to VIT plus 1 half AT squared only because the problem states that it is 4.7 meters above the ground. So I know that delta y here in this case would be 4.7 meters. And I'm just going to take the line of motion to be positive here. Okay. So I know VIT is going to cancel out because VI is 0 because it starts from rest. And then here I have just really 1 half AT squared. The question asks for time, so I'm going to keep the t squared term. I don't know what my acceleration is, so hopefully you've done some sort of practice regarding torque, but if you haven't, keep up here. So essentially I know delta y, I know the value for it. I don't know what a is, and I'm looking for t. So really the only thing that I need to find is a. So I'm just going to go ahead and do my algebra manipulation here. So I'm just going to go ahead and get t by itself. So to get t squared by itself, multiply both sides by 2 and then divide both sides by a. But you notice here this is t squared, you want t, so square root both sides. So essentially, to find t, I need to know delta y and a, and I highlighted a here because that is the only thing that's not given to me directly. So I'm just going to go ahead and set up my torque and Newton's second law. So I'm going to go ahead and draw the free body diagram here for all these, all the forces acting on the system. Here, the block on the left, that's f of g1. The red arrow is pointing down. So here, things are not drawn in scale, just to help you visualize where the forces go. Okay, here's f of g1 pointing down the page, and then there is a tension connected to this pulley. So because the mass of the pulley is not neglected, the tension on the left and right side will be different here. So I'm going to call this T1 just to keep the subscripts the same on the left side. But this portion of the string, there's also a T1 pointing down because it will cause the pulley to rotate. Okay, so the subscript here is going to be the same. So once again, the T1 pointing up, that's for the block. The T1 pointing down, that's for the pulley. And likewise on the right side, I'm going to go ahead and draw f of g2. F of g2 here is a little smaller because the mass was given as 18 and 11. So I know M1 is more massive, M2 is a little less massive. But once again, things are not drawn to scale here. Just to help you visualize. Here on the right side, this is going to be T2. T2 here is going to cause M2 to rise as M1 goes down. But likewise on the left side, there's a T2 pointing up for the block, but T2 is also acting on the pulley, but it's actually going to produce a clockwise torque. Okay, so T2 is going to be pointing down for the pulley. All right, other than that, let's go ahead and set up Newton's second law for M1 and M2. So to set up Newton's second law for M1, I just kind of box this here to help you focus. Well, M1 in this case is going to go downward, which implies that f of g1 is greater. So once again, I'm going to take the line of motion to be positive here. So I'm just going to say f of g1, which is m1g, minus t1. I'm subtracting because t1 for the block is acting against me. They're facing an opposite direction. And that which is equal to m1a. So you notice here the a does not have a subscript because the whole entire system is hooked to just one string. It will accelerate at the same rate. Okay, I'm going to go ahead and set up Newton's second law also for the second block on the right here. The m2 is going to go ahead and move upward, which implies that t2 is greater, and then f of g2 is acting against it. So I'm going to say t2, which is the force causing it to move in that line of motion, minus m2g, and that equals to m2a. But you notice here, m1 is given. I don't know what t is, and I don't know what a is. All right. Likewise in this term, the setup here. I don't know what T2 is, M2 is given, we know what G is, and we don't know what A is. So here you have two equations with two unknowns. So to solve for A though, you do need to involve torque because the mass of the pulley and the radius of the pulley here is given. Okay. So here I'm just going to set up net torque is equal to I alpha, but as you can see here in my diagram, T1, which will be larger, is going to cause the pulley to rotate in a counterclockwise direction, where my mouse is kind of circling in a counterclockwise direction there. So T1 will cause the pulley to rotate counterclockwise. However, T2 is acting against it, opposing it, will cause the torque here to be in the counterclockwise direction. So essentially, I'm just going to say T1 times R, because by definition, torque is just force times R that's perpendicular. And T1 here is already perpendicular at the junction here where it touches the pulley. All right, other than that, I'm going to subtract T2 times R. Again, I'm subtracting the two torques here because they're opposing each other. And on the right side, I alpha remains constant. So I'm going to go ahead and just extract the R out. Both these terms on the left side of the equal sign here has an R. I'm just going to factor out R. And then from there, I can go ahead and do a little manipulation. I know that angular acceleration is linear acceleration divided by R. Therefore, I can make that substitution. So that substitution is pretty vital here to help you find A really quick, which will allow you to finish this part A, hopefully in a timely manner. All right, but I'm just going to go ahead and cross that R out. There's an R there, and then there's also an R there, and then there's also an R square there. So if you think about it, if you move this R on the left side down to the right side, R times R is R square, but R square on the bottom and R square on top will cancel out. So I'm going to cancel all the R's out here. So therefore, it really reduces down to just T1 minus T2 equals 1/2 MA. Okay, so I don't know what T1 is. I don't know what T2 is. What I do know, though, is that I can use these two functions that I had set up for the two blocks M1 and M2 and isolate for T1 and T2 just to get rid of those terms. So here you just have a systems equation that you're just trying to juggle. Okay, so here on the left side, I'm going to go ahead and solve for T1. This is a negative T1, so I'm actually going to move it to the right side of the equal sign, which makes it positive. And M1A here is positive, so I'm going to move it to the left side, which makes it negative. So essentially, you have T1 is M1G minus M1 times A. And I want to do the same stuff here for the middle section here for T2. T2 is already by itself on the left side of the equal sign here, so to get it by itself, I'm actually just going to move M2G to the right side by adding it to both sides. So essentially, I have T2 is equal to M2 times A plus M2G. And then now that I have these two expressions for T1 and T2, I can just make a substitution in for here. So I color coded for you here. T1 is all this blue stuff, M1G minus M1A. And I put all that in parentheses here. So at this point, hopefully your algebra skill is good. You got to make sure you distribute this negative sign. If you don't distribute this negative sign, where my cursor is kind of going back and forth here, you're going to screw yourself over in terms of algebra skill. Okay. Here, I'm subtracting T2, but T2 itself is M2A plus M2G. So I like to go ahead and do my substitution using parentheses. And then as you can see from here, because both these terms are inside the parentheses and the negative sign is outside, you actually have to distribute this negative sign to both of these terms. So it's going to look like M1G minus M1A, okay, minus M2A, because I'm going to distribute this negative sign to the first term inside the green stuff here. That'll make a negative. But then that negative sign will also get distributed to the M2 times G. Well, it's positive. A positive times a negative makes it negative. So once again, be careful with your algebra skill here. So here, I highlight these two terms that has an A in it. Why? Because ultimately, I need to find what A is. There's an A here, there's an A there, there's an A on the right. So I'm just going to combine like terms. So I'm going to move both of these negative M1A and M2A to the right side and combine it with everything that has a linear acceleration. So both these negative terms move to the right side, become positive. So as you can see here, these three terms on the right has an A in it, so I can just factor out the A. So I can just say that 1/2 times the mass of the disk plus M1 plus M2 times A. Well, I know what M1 is, I know what G is, I know what M2 is, I know what G is, I know the big M, which is given, I know M1, M2. So really, as you can see, with a little bit of manipulation and a little bit of substitution here, the only thing unknown is your linear acceleration. So from here, I'm just going to kind of bring my work up here to solve for A. You need to divide the whole parentheses. So I'm going to move this 1/2 capital M plus M1, M2 into the denominator on the left side. And from here, it's just plug and chug. If you didn't read the problem, you want to read it. M1 is 18, G is 9.8. Once again, I take the line of motion to be positive, so G here is just a positive value. I'm subtracting from everything that acts against it, which is just the mass on the right side and times acceleration. But then this is the whole entire mass. And once again, the I value of a disk, in case you didn't keep up earlier, is 1/2 mr squared. A pulley is accepted to be a disk, so the I value of a disk is 1/2 mr squared, and that's where the 1/2 comes from, just in case I lost you there. Okay. Now, with a little bit of calculator work, you can just take my word for it, or you can just check my work. Hopefully I didn't screw up. Here I'm just going to plug in values. The 2 from this function gets carried down. Delta y, in this case, the line of motion is positive, so I'm just going to keep that as a positive 4.7. And then if you punch all this value that I'm going circling back and forth here with your calculator, you should get about 2.178. And then all you have to do is simplify that on your calculator. And then that'll give you about 4.316 underneath the radical, and then the square root of that will be about 2.077 seconds. So that is the answer for part A. Okay. Let's move on to part B. Part B asks you to find the net torque acting on the pulley. To do this one is pretty easy. Net torque is equal to I alpha. This is the easiest strategy to use, I think, because you already know what A is, and if you know A, you know alpha. And then I here, if the disk is pretty straightforward because you're given the mass of the disk, and then you're also given the radius of the disk. Okay. So once again, I'm going to break up into I into 1/2 mr squared, and then angular acceleration I'm going to resubstitute in for A over R. Once again, I'm using the strategy because I know everything. I just found what A is in part A, and M and R are given. So plug and chug time. Okay. Oh, excuse me. Before I plug and chug, this is mr square on top, and then there's an R on the bottom. So I'm actually just going to cancel out one of the R's on top. Okay. So I'm just going to carry down 1/2 mr times A. And there's the M of the disk is 5. The radius of the disk is 0.1. And then the acceleration I found previously in part A is 2.178. And then calculator work will give you a magnitude of about 0.5445. And then because it asks for net torque, in this case, it's telling us that M1 is going to go downward, which would imply that the disk is rotating in a counterclockwise direction. So therefore, counterclockwise in this case would be positive. Okay. Or in this case, if you'd like to say out of the board, if you're doing a vector analysis. All right. Other than that, that is the answer to part B. Part C. Part C, what is the kinetic energy of the pulley at 1.2 seconds? So it asks for just the pulley, so I'm just going to just set up KE for the pulley, which is just 1/2 I omega square. It's not moving linearly, it's just spinning around a some sort of pivot here. Okay, so the function for KE rod or KE rotational is just 1/2 I omega square. And then here, I'm just going to substitute out I is just 1/2 mr squared. The 1/2 in the front, that's just part of the kinetic energy function. And then I itself has another 1/2, so be careful with that. I'm going to go ahead and get rid of omega squared. So the relationship between omega and linear velocity is that V is equal to R omega. So if you isolate for omega, you get it's V over R, but this is omega squared. So you have to square the V and square the R. So R squared is going to cancel out, and then 1/2 times 1/2 is 1/4. So if you simplify all that, you'll get 1/4 mv squared. I know what the mass is. Mass is 5 kilograms. I don't know what V is though, but that's okay. I'm just going to set up linear kinematics real quick to find the linear velocity of the pulley. I'm just going to go ahead and use Vf equals At plus Vi. Okay, and then here I'm just going to go ahead and say that the linear acceleration is 2.178 meters per second squared times t, which is 1.2 because it asks for 1.2 seconds. And then if you simplify all that, you'll get that Vf is equal to 2.6136 meters per second. So here's the speed at 1.2 seconds. And once I know that, I can substitute in for V that I highlighted here. And don't forget to carry down the square term. So therefore, all this calculator work will give you about 8.54 joules. Okay, and that's that. The other alternative method that you can use if you like is to just go ahead and really start with the same statement, right? KE rotational is just 1/2 I omega squared. Okay. Therefore, I once again is broken down into 1/2 mr squared omega squared. However, I'm just going to go ahead and simplify this down. But then what I want to do here is that I just want to find omega. And so instead of getting rid of omega squared like I did using the last strategy, I'm just going to actually keep omega here. So using the same linear and rotational relationship, I know that the final angular velocity is equal to angular acceleration times time plus the initial angular velocity. But here, omega I is 0, so I'm just going to leave that out. Okay. But what I do know is that I do know that A tangent here is equal to R times alpha. So wherever this alpha is, I can just substitute it in for R alpha, so which makes sense. Okay. All right. So here, A is equal to R alpha. So here's alpha. So to get alpha by itself, divide both sides by R. I'm not sure why this should have been a capital R if you want to get technical, but it doesn't really matter. I wrote the function here just so you know the relationship between A and alpha. So A tangent is equal to R times alpha. So here in my work, I just got substitute out alpha for A over R, because to get alpha by itself, divide both sides by R. There it is. and the t gets carried down. Okay, the tangential acceleration or linear acceleration I already calculated in part A, which I just replug in there, and then the radius of the pulley is 0.1, which is given, and the time here is 1.2 seconds. So if you simplify all that, you get about 26.136 rats per second. And then now that I know omega, I can just really just plug it in back to my original statement here. So here, it's 1/2 gets carried down. The 1/2 as part of the moment of inertia gets carried down. The mass of the pulley is 5. The radius of the pulley is 0.1. I want to square that. And then I want to times it by the angular speed at 1.2 seconds, which I just found to be 26.136. And I want to square that. And all that on your calculator will also give you a value of 8.54 joules. Okay, so that's the answer to part C, using the other way if you don't want to use V linear. Now, part D asks you, how would your answer to part A change if the mass of the pulley were neglected? Okay, well, part A asks us to find the time that it takes for M1 to hit the ground. Okay, so in this case, if the mass of the pulley was neglected, right? So if it sets like a problem, if the problem sets the mass of the pulley is negligible and all that good stuff, well, if the mass of the pulley is neglected, there's less mass involved in the system. If there's less mass, and then you have your two masses here that are constant, the acceleration will actually increase. The system will accelerate faster because there's less mass involved. Well, if you accelerate faster, you'll cover the same distance in less time, right? Which I think makes sense. You know, if you have a car that accelerates super fast versus an older car that accelerates slower, the fast car will complete a certain distance in less time because it gets up to speed faster. So in this case, the answer part D will be the time will decrease because the acceleration in the system increases, which allows you to cover the same distance in less time. All right, I hope that helps. Stay nerdy, don't be whack.